The chapters of this volume have toured the planets one by one, from scorched Mercury to the frozen worlds beyond Neptune. This chapter does something different. It holds them up against one another. Comparative planetology is the discipline that treats the planets not as a catalogue of unrelated worlds, but as members of a single family, whose very differences are the most valuable evidence we have. Rather than describing each planet in isolation, it asks why they diverged, why the Earth alone has oceans and drifting continents, why Venus, the Earth's near twin in size, runs a furnace hot enough to melt lead, why Mars froze and lost its air, why Jupiter and Saturn glow with more heat than they receive from the Sun, and why the strength of planetary magnetism ranges over a factor of 1,000 from Mercury to Jupiter. The wager of the method is that all the planets are variations on the same shared physics, so that the cleanest way to understand any one of them is to ask why it differs from the rest. The power of the approach lies in controlled comparison. Hold one variable fixed and read off the consequences of the others. Venus is most illuminating when set beside the Earth, with which it shares mass and radius almost exactly, yet from which it diverges catastrophically in climate. The comparison isolates everything that is not size. Mars is most illuminating beside both, the small world that began wet and ended frozen, its story a lesson in the consequences of mass. The giant planets form their own comparative axis, the gas giants Jupiter and Saturn against the ice giants Uranus and Neptune. And the airless bodies, Mercury and the Moon, form a third, on whose surfaces a 4-billion-year record of impacts survives that air, water and tectonics have erased everywhere else. Reading each world against its siblings rather than on its own is what lets the same handful of physical processes, tuned differently in each case, explain the whole diverse family. Everything begins with the bulk parameters, the mass and the radius, because they are measured to exquisite precision from the way a spacecraft's orbit responds to a planet's gravity, and because from them follow the density, the surface gravity and the escape velocity that frame all else, and the density alone tells the central story of the solar system's architecture. The 4 inner planets all exceed 3,900 kilograms per cubic meter, the signature of rock and metal. The 4 giants all fall below 1,700, the signature of hydrogen, helium and ice. The Earth is the densest planet of all, and Saturn the least dense, so slight that its average density is actually less than that of water, which means the old classroom claim that Saturn would float, were there an ocean vast enough to hold it, is quite literally true. That single column of numbers, the densities, cleaves the planets into 2 great families and points straight at how and where each of them was built. Raw density, though, is misleading, because gravity crushes a planet's own interior, so that a more massive world is denser simply from the weight of its own overburden. To compare what planets are truly made of, one corrects to the density the material would have, with the compression removed, and at that point a surprise emerges. Mercury, whose measured density nearly matches the Earth's despite its being 1/14 of the mass, reveals itself as the iron-richest planet of all, with a metallic core filling some 85% of its radius. The interior beneath the surface is probed by a still subtler measurement. The way a rotating planet's gravity departs ever so slightly from that of a simple point mass yields a single dimensionless number that measures how strongly its mass is concentrated toward the center, 2/5 for a uniform sphere, and lower for any world with a dense core. This number, extractable from nothing more than the Doppler shift of a passing spacecraft's radio signal, is the comparative planetologist's sharpest probe of a world one can never cut open. Across the family, planetary interiors arrange themselves along a continuum set by 2 things: the mass a planet gathered as it formed, and the temperature of the disk at its birthplace, which fixed what could freeze into solid there. Inside the snow line only, rock and metal were solid, and so the inner planets are dense balls of rock and iron. Beyond it, water and other ices were abundant, letting large solid cores grow fast enough to seize hydrogen gas before the disk vanished. The terrestrial planets share a common architecture, a metallic core, a rocky mantle and a thin crust, but in strikingly different proportions, from Mercury's outsized core to the Earth's more modest one. And a terrestrial planet's size largely decides its fate, for a small world has more surface, for its volume sheds its heat quickly and freezes solid, while a large one holds its warmth for billions of years. This is why Mars, at 1/9 of the Earth's mass, has a cold, dead interior, while the Earth remains geologically and magnetically alive. The gas giants are built outward from a heavy center through a vast envelope of hydrogen. which under the crushing pressures deep inside is squeezed into an exotic liquid metallic state that conducts electricity like a metal, before thinning to ordinary molecular gas near the cloud tops. The defining modern discovery from NASA Juno spacecraft is that Jupiter's center is not the compact ball of rock and ice that older models assumed. Juno measured the giant's gravity field to unprecedented precision and found it incompatible with any sharp core. The data instead demand a dilute, or fuzzy, core, in which the heavy elements are smeared out and blended into the surrounding hydrogen, extending to well over half the planet's radius. This astonishing result blurs the once clean boundary between core and envelope, and it bears directly on how Jupiter formed. Either its core never fully gathered itself together, or convection and early giant impacts stirred an initially compact core outward through the hydrogen over the ages. Either way, the interior of the solar system's largest planet is stranger than anyone expected. The ice giants Uranus and Neptune are a genuinely distinct class, and among the least understood objects in the solar system. Their densities imply interiors dominated not by hydrogen gas, but by a hot, dense, electrically conducting fluid of so-called ices, water, ammonia, and methane, wrapped around a small rocky core beneath a comparatively thin skin of hydrogen and helium. The trouble is that we cannot pin the interior down. Each planet was visited only once, by Voyager 2 in a single brief flyby decades ago, so the gravity data are sparse, and the behavior of warm, dense water at the pressures found inside these worlds is still being worked out in shock compression laboratories and supercomputer simulations. Whether their interiors are neatly layered, or fully mixed, or contain a deep gradient of composition that stifles convection, remains an open question, one that bears directly on their strange magnetic fields and their puzzling heat flows, and one that is the primary scientific motivation for sending an orbiter to Uranus in the decades to come. Nowhere is the comparative method more vivid than in the atmospheres of the three sibling worlds of the inner solar system. Venus, the Earth, and Mars very probably began with comparable stores of water and gas, delivered as they formed, yet they occupy three utterly different climates. Today, a hot, dense, bone-dry inferno, a temperate ocean-bearing balance, and a cold, thin near vacuum. The governing physics is the balance between the sunlight a planet absorbs and the heat it radiates away, with greenhouse gases trapping some of that outgoing heat. Without any atmosphere, the Earth would sit below freezing. Its greenhouse gases lift the surface a life-giving 30-odd degrees to a global average around 15 degrees Celsius. Venus shows the same physics carried to a monstrous extreme, its surface roasting at 737 Kelvin, over 460 degrees Celsius beneath 92 atmospheres of almost pure carbon dioxide. It is, remarkably, the hottest planetary surface in the solar system, hotter even than Mercury's, despite lying nearly twice as far from the Sun, because its thick blanket traps the heat that airless Mercury radiates straight back to space. The Venusian inferno is understood as the end state of a runaway greenhouse. If a planet with surface water absorbs sunlight above a critical threshold, then rising warmth evaporates more water, and water vapor is itself a potent greenhouse gas, so the temperature climbs further, which drives yet more evaporation, in a feedback that does not halt until the oceans have boiled entirely into the sky. Once the water is aloft, sunlight splits its molecules, the light hydrogen escapes to space, and the runaway becomes effectively irreversible. The smoking for this history is written in the isotopes. The heavy form of hydrogen, deuterium, is enriched in what little water remains in Venus's atmosphere to about 150 times its abundance in the Earth's oceans, exactly the fingerprint left when the lighter hydrogen of a vast primordial ocean escapes preferentially over the heavier deuterium across billions of years. Venus, in short, once had an ocean's worth of water, and lost it all to a thermal catastrophe that turned a possibly temperate world into the solar system's furnace. Mars illustrates the opposite fate, governed by a different variable, size. It keeps only the thinnest wisp of an atmosphere, a surface pressure under a hundredth of the Earth's, yet dry riverbeds, deltas and water-formed minerals show that it was once warm and wet enough for flowing water. Two things doomed it. Its small mass made its gravity too weak to hold its air firmly, and its small size let its interior cool and its magnetic dynamo shut down, so that, stripped of the global magnetic shield that protects the Earth, its upper air was slowly eroded away by the solar wind, a loss the Maven spacecraft has watched in progress. The three outcomes form the lesson entire. Venus was too close to the Sun and lost its water to a runaway. Mars was too small to hold its air, the Earth at the right distance and the right size, and equipped with a slow geological thermostat regulating its carbon dioxide, threaded the needle between them. From this trio comes the very concept of the habitable zone, the band of distances where a world of the right size can keep liquid water, now the organizing idea in the search for life beyond the solar system. The giant planets reframe the whole balance because they have no surface and are heated as much from below by their own internal warmth as from above by the distant sun. Their banded, jet-streaked skies are driven substantially by heat convecting upward through a deep, fast-spinning fluid interior, rather than by the equator-to-pole gradient of sunlight that stirs the weather of the rocky planets. Rotation organizes the flow into a pattern of numerous, swift, remarkably durable east-west jets, and the turbulence of small storms feeds energy upward into these broad bands rather than dissipating it. It is this deep, rotation-dominated regime that sustains structures of astonishing longevity, above all Jupiter's great red spot, a storm larger than the Earth that has raged for centuries. The contrast with terrestrial weather is itself a comparative lesson. The same fluid physics, given a deep atmosphere, rapid rotation and heating from beneath rather than a thin shell heated from without, produces a completely different and far more stable pattern of winds. 6 of the 8 planets generate global magnetic fields by dynamo action deep inside them, and the comparison across these fields is one of the triumphs of modern planetary physics. A dynamo needs 3 things: a region of electrically conducting fluid, convection to stir it, and rotation to organize the stirring, and where that conducting fluid sits, liquid iron in the rocky planets, liquid metallic hydrogen in the gas giants conducting ionic fluid in the ice giants, shapes the field it produces. The strengths span a 1,000-fold range. Mercury's field is astonishingly feeble, a mere 100th of the Earth's at the surface, yet it is a genuine active dynamo, which is itself a puzzle for so small and slowly cooling a world. The Earth's field is moderate and steady, and Jupiter's is the giant of them all, the strongest in the solar system, generated in a shell of metallic hydrogen larger in volume than all the other planets put together and stirred by the fastest rotation of any planet, under 10 hours. From Mercury's whisper to Jupiter's roar spans that factor of 1,000. The shapes of the fields cluster into families that are themselves diagnostic. The Earth and Jupiter have fields dominated by a simple bar magnet form, tilted about 10 degrees from the spin axis, with prominent patches and a slow change over time that spacecraft can now track, at Jupiter as well as at home. Mercury and Saturn are strikingly different, their fields almost perfectly aligned with the rotation axis, Saturn's, to better than a single degree, an alignment so perfect that theory says it should be impossible for a self-sustaining dynamo, and which is usually blamed on a layer of raining helium deep inside that filters out the tilted components. The ice giants are the true outliers. Voyager found the fields of Uranus and Neptune to be wildly lopsided and tilted, Uranus's magnetic axis leaning some 60 degrees from its spin axis and badly off-center, Neptune's nearly as strange. Geometries thought to arise from dynamos operating in a thin shell of conducting fluid rather than throughout a deep core. Each planet's field in its shape as much as its strength reports on the hidden region that makes it. The unifying prize is a scaling law. Analyzing a great suite of computer simulations of planetary dynamos, Ulrich Christensen and Julian Orbit showed that the strength of a planet's field is set remarkably, not by how fast it rotates, but by how much heat is convecting through its conducting region, the field's energy tracking roughly the cube root of that heat flow. That the rotation rate should drop out of the law was a genuine surprise, and its triumph is that a single relation reproduces the measured field strengths of planets, and even of rapidly spinning small stars across many orders of magnitude in size and strength. It is the closest thing comparative planetology has to a unifying equation, and it explains at a stroke one of the deepest comparative facts of all. A vigorously cooling, convecting Earth generates a strong protective field, while a frozen, quiescent Mars cannot, and that matters far beyond the physics of the fields themselves, for each field anchors a magnetic shield that deflects the solar wind, and its presence or absence is one of the threads running through the climate divergence of Venus, the Earth and Mars. On worlds with little or no atmosphere, the surface itself is a recording medium 4 billion years deep, and impact cratering is the universal clock that reads it. The logic is simple and powerful. A surface exposed for longer accumulates more craters, so counting the craters on a patch of ground dates that ground, provided one knows how fast impactors arrive and how the size of an impactor maps to the size of the crater it digs. The method works because the impacting population is largely shared across the inner solar system, most of it flung from the asteroid belt, so the crater records of the Moon, Mercury, Mars and the rest can be compared on common terms. The essential calibration comes from the Moon, the one body whose crater densities can be tied to the precisely measured radiometric ages of the Apollo rock samples, giving an absolute chronology. That lunar clock is then carried to the other planets, with careful corrections for each world's gravity and impact speed, which alter how large a crater a given impactor makes. From this single tool flows the dating of nearly every ancient surface in the solar system. Reading surfaces against one another also exposes the processes that erase craters, and those processes are themselves diagnostic. The Moon and Mercury are saturated with craters because nothing removes them. Their faces are essentially fossils, preserving the record whole. Mars stands in between its ancient cratered southern highlands, giving way to younger volcanic plains and water-carved valleys, the mark of a world that was geologically and hydrologically busy early on and then largely shut down. Venus is the striking exception among the rocky planets. It bears relatively few craters, scattered at random, with almost none small, and little sign of gradual wear, a pattern read as evidence that the entire planet was resurfaced a few 100 million years ago, perhaps in a catastrophic volcanic overturn that wiped the older record clean. And the Earth uniquely preserves the fewest craters of any rocky planet, not because it was spared but because its oceans, its weather and above all its drifting, subducting plates continually recycle and renew its crust, swallowing the scars of impact almost as fast as they form. That last point opens the deepest comparative distinction of all. Every rocky planet must shed its inner heat, and the way it does so divides the terrestrial worlds sharply. For the Earth's mode, plate tectonics is seen nowhere else. On most rocky bodies the cold outer shell is a single rigid lid capping the churning mantle beneath, heat escaping only by slow conduction and occasional volcanoes. This stagnant lid is the state of Mars, Mercury, the Moon, and it seems Venus today. Only on the Earth is that shell broken into plates that are themselves cold and dense, so that where a plate becomes heavy enough it plunges back into the interior, dragging the surface down with it and letting the planet cool far more efficiently while endlessly recycling its crust. Why the Earth and Venus, near twins in size and makeup, took such different paths is a central puzzle. Venus's great heat, and perhaps its loss of water, may keep its rocky shell too soft and buoyant to break into sinking plates, leaving strong, hot Venus locked under a stagnant lid while cooler, wetter Earth slid into the mobile dance of plate tectonics. A planet's energy budget, what it absorbs from the sun against what it radiates and generates within, is a sensitive probe of its interior, and here the giants reveal processes invisible from their composition alone. The rocky planets emit essentially only what they absorb, but all the giants, except one, radiate substantially more energy than they receive, roughly twice as much. For Jupiter this is simply leftover heat. The planet is still slowly shrinking under its own gravity, 4.5 billion years on, converting gravitational energy into radiation, and a contraction of no more than a millimeter a year suffices to supply its glow. Saturn poses a lovely puzzle, for it radiates even more excess than simple cooling allows, and the answer is that deep inside it helium becomes unable to mix with the metallic hydrogen, condenses into droplets and rains toward the center, releasing gravitational heat as it falls. And Uranus is the conspicuous exception, emitting almost no more than it absorbs, its internal heat flow mysteriously feeble, far below its near-twin Neptunes, an unsolved anomaly that a deep barrier to convection or an ancient catastrophic impact may explain. The dynamical state of a planet, how fast it spins, how far its axis is tilted, and the shape of its orbit is the third great pillar of comparison. Because rotation organizes the dynamo and the weather, tilt governs the seasons, and the orbits record the system's formation. The spins vary enormously, from Jupiter's 10 hours to Venus's 243 days, the slowest of any planet and uniquely backward. Mercury, meanwhile, is locked in a precise rhythm, turning exactly 3 times for every 2 of its orbits. The axial tilts are just as telling, near zero for Mercury, a moderate 20-odd degrees for the Earth and Mars that gives them their familiar seasons, but a full 98 degrees for Uranus, which lies tipped entirely onto its side. its poles taking turns to point almost straight at the Sun through its long orbit. The Earth's own tilt is held steady by the Moon, one more entry in the list of fortunate circumstances that comparative planetology links to its lasting habitability, while the orbits themselves, near-circular and near-coplanar, are a fossil record of the disk from which the whole family formed. The deepest justification for this whole enterprise has shifted in the last 30 years. Comparative planetology began as a way to understand our own 8 planets by reading their differences. It has become as well the calibration set for the rest of the galaxy. Thousands of planets are now known around other stars, and they have shown that the solar system is but one architecture among many, and often not a typical one. Yet our own system remains uniquely precious, for it is the only one we can study up close, with spacecraft that measure a planet's gravity, its magnetism, and the isotopes of its air directly. Every relationship calibrated here becomes a tool for reading worlds we will only ever glimpse as a flicker of starlight. The mapping of density to composition, applied to a distant planet's mass and size, reveals whether it is rock or gas. The dynamo law predicts whether it can raise a protective field. The runaway greenhouse calculation that explains Venus defines the inner edge of the habitable zone around another star. The solar system is the Rosetta Stone, the one place we can ground truth the physics before applying it blind. It is worth being honest, too, about what remains unknown, for the discipline has a long list of open questions. The interiors of Uranus and Neptune are genuinely uncertain, constrained by only 2 fleeting flybys, and a Uranus orbiter is the highest priority of current planetary roadmaps precisely because these questions cannot be answered from afar. The reality of a late, intense bombardment of the young planets is still debated. The detailed story of how Venus and the Earth diverged, whether Venus ever had oceans, and when its runaway struck, is the target of a new fleet of missions now approved. And the master question that quietly organizes the entire field, what combination of size, distance, composition, and dynamical state makes a world habitable, and how special the Earth's own combination truly is the very question the comparison of Venus, Earth, and Mars was always implicitly asking. The enduring lesson is the one with which we began. The Earth's oceans are legible only beside Venus's furnace and Mars's frost, Jupiter's dilute core only beside Saturn's helium rain. Comparative planetology is the practice of holding the worlds up against one another until their differences explain themselves, and of recognizing in the end that the same few physical processes, tuned by mass and distance and time, wrote every one of their very different stories.